Hello and welcome to this talk on improving debug variable location coverage. Anecdotally, we're often told that LLVM doesn't do very well at producing debugging information, and the usual symptom is that when you inspect your variables when stepping through your code in a debugger, you're typically told that they've been optimized out, and apparently this happens much more often with LLVM than it does with other comparable compilers. So this talk is about improving that situation, improving location coverage. What are variable locations? Well, here's an example in this slide. On the left-hand side, I've got some contrived C source code where I've put some boxes around the variables in the program. Down the middle is the x86 assembly that it compiles to, and on the far right-hand side is the variable location table, listing for each variable, for each instruction, which register it is located in. And hopefully you can see that it's fairly complicated. Variables can be in different registers, they can move around, and they can be optimized out. They can have no location from certain points onwards. How does LLVM represent this internally? Well, we have the debug value intrinsic, which is used to record facts. There's a lot of metadata in the slide, which we just don't care about. The only important parts are that each debug value intrinsic has a position and it has a value in the program. For example, the one at the start is at the very start of the program, and it's referring to %bar, the first argument to the program. This is, it's good enough to describe all the optimizations in LLVM. It becomes trickier when we get to register allocation and we then have to lower down these values into being register locations. And we're going to take a dive in and look at what problems that presents, stopping first of all immediately after instruction selection to observe how variable locations are recorded in mir after instruction selection runs. It's pretty much the same. Instead of intrinsics, we have a debug value instruction, which has a position in the program, and it refers to a virtual register. At this point in compilation, the virtual registers are in SSA form, so each one is one unique value. Now, when the register allocator runs, the virtual registers will subtly change, and they will be locations now, and they can be defined by multiple different instructions in different places. And this presents a difficulty where we have to ask ourselves, when a debug value refers to a virtual register, what value within that virtual register is it referring to? Let's zoom in on just a few specific instructions and examine that. Looking at this slide, at the start, we are reading in the argument value from EDI to the function into virtual register 0, then copy virtual register 0 to virtual register 2. Virtual register 2 is fed into an add instruction, which both reads and writes to virtual register 2. And virtual register 0 is used by a debug value saying at this point, the BAS variable is assigned the value of virtual register 0, the input argument. Right now, the program is unambiguous as far as debugging information is concerned. But the next thing to happen is the register coalescer runs, and it can notice that that middle copy is redundant. We can merge together both those virtual registers, 0 and 2, and we have a question for the debug value instruction there. Will the merged virtual register still refer to the same value as the 0 virtual register does beforehand? Now we can look at this, the result of the register coalescing, and see that once these two registers are merged together, we're going to have code where the argument is copied into virtual register 2, that's fed into the add instruction, where it's clobbered and eradicated. And so there is no virtual register in this coalesced program that still contains the argument value. There's nowhere for the debug value to point, no register for it to identify. So we change its operand to no reg and say it's been optimized out past this point. That's the correct thing to happen in this case because an optimization has legitimately eliminated that value from the program. But it's very difficult to do this in the general case. It all comes back to that question that I posed of, at the point of this debug value, what value is it that its virtual register operand contains? And that's actually quite challenging to determine. Let me illustrate by drawing on the live ranges that the register allocator keeps as it's compiling the program. These are on the right-hand side, and we see that virtual register 0 has a range over the first couple of instructions where virtual register 0 is live. And then the virtual register 2 is live from the second instruction onwards. Great. And those live ranges contain the values that each virtual register contains. Now, at the point of the debug value, when the coalescing starts to happen, we will say virtual register 0, what value is it that it contains here, so that we can work out whether it still does after the coalescing. You look at the debug value, you look to the right to see what is the live range, and there is no live range. The register allocator does not track that live range over the debug value instruction because the virtual register is not live. So we can't work out what value is in the 0th virtual register at all. Why is this the case? Well, the register allocator, it's only interested in the interference between virtual registers so that it can identify whether or not it can merge them, whether it needs to split them up, whether it needs to spill them, and so forth. It doesn't keep around all information about all virtual registers at all points of the program. Whereas for debugging information to be accurate, we need and want full dominance information. We need to know at the point of that debug value instruction what is the last dominating assignment to virtual register 0. And that is simply not available because the register allocator does not keep that information around. We can't guarantee whether or not there will be whether a virtual register will exist after merging containing the right value. And so out of conservativeness, we have to drop this variable location and mark it as optimized out. Not because it's optimized out, but because we can't really tell. And there are scenarios, even with this small bit of code, where it would be legitimate to keep that variable location. If I put a branch in after the copy that's going to be coalesced, then we'll place the clobbering add instruction in its own block, block 1, and the debug value is in its own block by itself, where it's still referring to the virtual register. Now on all paths from the start of the function into block 2, where the debug value is, the virtual register is still going to contain the right value, the argument value, and it would be safe to keep this debug value referring to the merged virtual register. But we can't work that out, so we have to drop it out of conservativeness, which is unfortunate. It's also not as simple as just being a matter of missing a few instructions where the value is out of liveness. In addition, the liveness of virtual registers can be shorter, much shorter sometimes, than the values they contain. Due to the way that machine instructions and blocks are generated, there are sometimes redundant copies inserted that are then register allocated away at a later date, but debug values can end up referring to the wrong virtual register, as it were, which happens to be out of liveness at the wrong moment, and the value has gone and lived in a different virtual register. Those debug values will end up being dropped. In addition, some register allocation constraints are encoded in copies. We can have copies from general purpose registers to specific virtual register classes to represent the fact that a particular value has to be in a particular kind of register. In those cases, the value continues to live on after the copy and before the copy, but we may have a debug value referring to the wrong virtual register, which is now artificially dead, even though the value is still alive. And we will drop those debug values, which is unfortunate. Now, the natural question at this point is to say, well, can't we just look back a few instructions, work out what the virtual register used to contain before it went out of liveness, and then work things out from there? Which is tempting, but that isn't a general and efficient solution, because in the presence of arbitrary control flow, we can't guarantee that this is the case and work it out. We might end up searching the whole function to work out what the old value used to be. There's actually an analogous problem which I think we can compare this to, and that is compiling a C program before it's put into SSA form. If we go back to the code we were looking at before, the contrived C on the left, imagine, let's take the subtract operation, and let's say we have a machine where there's a very fast subtract instruction, but it's only really fast when all of its operands are positive. We would need to guarantee that the operands are positive, and in this code, the operands are crux and x, y, z, z, y. But in C, variables are locations. They can have multiple values assigned to them. And so to guarantee that the operands are going to be positive, you have to look back through the source code from the point where the subtract operation occurs and work out what values are assigned and whether or not they're positive or not. Looking back through the program, potentially through arbitrary control flow, it's much like the problem I just described with the register coalescing. LLVM's solution to this, of course, is to put the C program into SSA form, so that for any operation we can just look and say, well, the operands are these values, and we can determine things about these operands. I think hopefully you can see where I'm going with this. Why don't we do the same thing with the debugging information? Look on the right-hand side of this slide. Instead of referring to the virtual register that contains a value, why don't we refer instead to the instruction that defines that value? That way, the virtual register can be changed and the debugging information doesn't need to think about it. This does push back the problem of working out what register a variable is living in until later in the compiler, but that's something we'll get to in a few more slides. So then, a new technique that doesn't refer to virtual registers in the debugging instructions, I've been calling it instruction referencing. A better name would probably be value tracking, but that was already taken. And we'll look at an example of it now. We're going to take the C code in the middle of this slide. Imagine we have a variable that is assigned, we have a branch, and on either side of the branch, the variable is assigned again. Then control flow merges into a block where the variable is returned, right? On the left-hand side of this slide, we have the x86 and debugging information as produced nowadays. We have, in the entry block, a load of a constant value into a virtual register, %0. We then have a debug value referring to the virtual register %0. Okay, fine, that's how things are nowadays. How would we do this with instruction referencing? Look to the right-hand side of the slide and look at the entry block there. We have the same load of a constant value into a virtual register, but we've put a label on it this time saying that it is instruction number 1. And then the next instruction below, when we want to refer to that value, instead of referring to the virtual register, we say instruction number 1, operand 0. In effect, we are indirectly describing the position of the operand within the instruction without referring to the register itself. We're just adding another level of indirection. And the benefit of this approach is that the register allocator can come and rewrite the registers in this program to its heart's content, really go crazy, and the debugging information doesn't need to care at all. It does have some limitations with this new approach. The first of all is there's a little more work required when optimizations happen to the instructions as opposed to the registers. Let's imagine, say, that this load of a constant value is replaced by an instruction that loads multiple constant values. In this slide from top to bottom, instead of loading 0 into %2, let's load constants 42 and 0 into registers rex and %2. All right. We had an instruction reference, a debug instruction reference to instruction 3 operand 0, but that's now invalid because that instruction has gone away. We now have instruction 4, and the value we're aiming to describe is in operand 1 now, not operand 0. My approach to this is let's just record a list of substitutions that have happened during optimizations. So at the bottom there's a list. It is what was instruction number 3 is now, with operand 0, is now instruction number 4 with operand number 1. It's just a big table of substitutions. This requires a little more work of instrumentation through the compiler, but I think it's going to be worth it in the end. There's another limitation when it comes to phis. Phis in LLVM are instructions. They're instructions through most of the CodeGen backend as well, until we hit the register allocator, which allocates them away. They become implicit, and they are the joining of control flow on the entry to a block at a particular register location. And there isn't now an instruction that we can label with an instruction number for them. My solution to this is to insert debug phi instructions indicating at the start of a block, here is a physical register where that phi occurs, and we give it an instruction number at that position, so we can still refer to the value that's computed in that place. This slightly compromises the model I was aiming for because I didn't want to refer to registers using the debugging instructions, but it's low risk. These are only inserted after register allocation and all kinds of register optimizations have occurred. It's very difficult for later optimizations to dislodge a phi at the start of the block from existing or to optimize it away. So slight compromise, but much lower risk of losing coverage or having wrong coverage as a result of this representation. Now, let's imagine that we've reached the end of compilation. We still have these references to values in the debugging instructions. We need to map them onto register locations. And I'd like to make an observation that we're really at this point dealing with two different functions. And I've separated them out on this slide. On the left-hand side, we have a function of machine instructions where there are assignments to register names. And on the right-hand side, we have a variable value function where there are assignments to variable names of values. And each of them share the same control flow. And each of them are defined over the same language. We still have the instruction numbers and operand numbers that we've been labeling things with, and we can join the two together using that common language. We just need to work out for each instruction in each block what's the desired value for the variable and what locations, what registers contain the desired value. And we can work that out just by applying existing SSA algorithms that are completely bog standard. Let's apply it on the left-hand side first. What values are assigned into the REX register using the instruction and operand numbers? Apply some SSA, and we get this representation. We know that in the entry block, REX is assigned value 10. On either side of the branch, it's assigned 20 and 30. That's instruction number 3, operand 0, as it were. And on the join into the return block, we have a phi where value 20 and 30 join together in the position of REX. Okay, great. What about the variable value assignment program? Well, we can run exactly the same analysis again. We can say that in the entry block, the variable is assigned value 10 on either side of the branch, 20 and 30, and then they join together in the return block, a phi between value 20 and value 30. Now, to map one back to the other is just a case of looking at this and saying, take the entry block. The variable is assigned value 10. Where is value 10? Look on the left-hand side. In this block, it is located in the REX register. So the location of the variable in the entry block is REX. Exactly the same approach for either side of the branch. Slightly more difficult for the phi, in that we need to seek out in the phis that exist in the machine function a phi that represents the joining of the two values that the variable wants to join, values 20 and 30. But we can see that there is such a phi in the REX register in this example. If there wasn't an appropriate phi, or indeed at any point in the machine function there was no value that was desired in any register, we would just say, well, at this point, there is no location for this variable. It is optimized out at this point, and there is no register location at all. So that is the overall view of this new technique. Let's refer to variable values by referring to their defining instructions and avoid thinking about registers at all up until the end of the compilation at the point where we start examining. We can use SSA to solve these problems. Hopefully you'll take it on faith from me that we can just apply SSA and it works for all kinds of control flow. It's a generalized algorithm after all. We also need to run a little bit of value propagation to eliminate any unnecessary phis that might have been introduced, which is just the same as memtoreg does at the other end of the compiler. Now, is this beneficial for variable location coverage? Well, we've compiled a few bits of game code and Clang in stage 2 to try and work that out. And we see that of all our variables, there's an improvement in the number that have location attributes attached to them. One game it goes up by 3% and another 6%. In Clang, a modest 1.3%. And for I've also been calculating the probability that you have of seeing any particular variable. If we take in a binary every variable that there is, every byte where it's in scope, and take the aggregate of the probability of whether or not that byte is covered by a location attribute, then we can see that there's a huge aggregate. In the first game, we have an improvement from 78% probability to 81% probability of seeing a particular variable. In the second, it goes up from 75 to 79. And for Clang, there's a modest 1% improvement because Clang, at the start, it had a high base. It already had fairly good coverage for the variables in the program. So that's my new technique. I look forward to answering any questions you have in the question and answer session after this is broadcast. Thank you.
Thank you, Jeremy, for this fantastic talk and for explaining both the problem and the solution so well. Reminder for everybody in the audience to please post your questions that you have for a speaker. While we're waiting for the first questions to arrive, I have one question of my own. Can you explain and elaborate a bit about the current state of the implementation and what the next steps are for adopting this in LVM?
Current state is that it's in tree at the moment. It can be enabled by someone passing xclang at experimental debug variable locations to the Clang driver, which will enable it all throughout. It's supported on x86. It works on AArch64, but there's been less testing going on there. And it works fairly well. Hopefully in the next couple of weeks, I'll have updated all of the tests to correctly reflect new behaviors and new internal representations with the new representation, and also to switch it over by default, which so far has been met with approval in an RFC on the mailing list.
That's great to hear. Is the implementation tied to a particular instruction selector, or does it plug in after the instruction selector?
It's at the moment limited to selection DAG. There's no reason in principle or no specific connection with selection DAG. It would be easy to implement it for global ISAR, for example. It's followed almost exactly the same techniques through selection DAG, which are used in global ISAR as well. So I think there'll be a very simple mapping of one onto the other, because at that point in the program, everything is still in SSA form, of course.
Paul is asking, does this tend to reduce the overall number of debug instructions? I'm curious if this would be a step in the direction of removing debug instructions entirely.
It is a step in that direction. At the moment, every single variable and every assignment to a variable is represented by one instruction in LVM, or one instance per variable and per assignment, which is many times inefficient and awkward, but it's been difficult to remove them from the instruction stream because you need to have an instruction that contains an operand that can refer to a virtual register. And by separating out the virtual registers and the debug information, it is now, in theory, possible to pull the debug information out of the instruction stream. It still needs to have some kind of position to mark out where an assignment occurs, but that doesn't have to be an instruction. It could be represented in some other way.
Kyung Woo asks, I wonder what the build time overhead is.
Good question. There is some, I'm indebted to the LLVM compile time tracking project, which runs CTMark, if you ask it too nicely. At the moment, there's something in the region of 3 to 4% additional compile time for a variety of things in CTMark. There's a link to this in my RFC on the mailing list. And this partially is down to the fact that more dwarf is produced. The file sizes are between 5 to, I think one of them is 20% larger, excuse me. And so just with producing more information, there is going to be more time taken consuming it. It isn't completely optimized yet, and it is more accurate, so there is just an extra cost. I'm having to get it down to less than 1.5%.
I'm curious, did you also measure the memory overhead for the additional IR and metadata that we're tracking?
It shouldn't be. So very kindly, Caroline from Google did some testing on this and didn't observe an increase in memory usage. And ultimately, it should, in the long term, lead to a reduction when we're able to compress debugging information and all of those many debug instructions that were mentioned all together into one. So nothing observed that's bad in the short term, and in the long term, this should lead to a bigger improvement.
Okay. Thank you very much, Jeremy. We're at the end of our time. This was a great presentation, and thanks for all the great questions to the audience.
Cheers.